All right, so this little problem here is not as useful as it once was, but this is very, very much the kind of thing that the lovely ladies who landed us on the moon would do as calculations. So log base b of 24, log base b of 4/9. Like the b might be 2, might be 3, like those were very common bases. But you wouldn't have a log base 2 of all the integers. You would actually just get log base 2 of the prime numbers. And this is because of prime factorization. So 24 is what we call a composite number because I can break it into a product of smaller things. And that is what we're going to do on these. And we're going to see that the result is all stuff that can be written in terms of log b of 2 and log base b of 3. In the homework, they might also give you log base b of 5 or log base b of 7. Those are the next. And then the number you'll see inside will be some product of those. So that is the first thing we're going to do is take a step to the side and figure out, well, what the heck is 24? I know that. That's 6 and 4. My 6 is a 3 and a 2. My 4 is a 2 and 2. You also could have done 2 and 12 and gone from there. So 24 is 2 to the third times 3, or 3 times 2 to the third. The order doesn't matter, but that's what we want our next line to be. So in order to make use of my expansion rules, I need to break this down into something that is a product or a quotient. But now see, the number parts in there are the 2 and the 3 we had. So I know what to do with that product. We're going to split that into a sum. So I have log base b of 2 to the third, which, yes, the next step will be power down, and log base b of 3. Now, when you do a bunch of these, like over and over and over again, then you get to the point where you don't have to write every single step. But you have to be pretty comfortable in order to do that. So there's nothing wrong with being careful. We don't have time to, oh my gosh, figure out the answer quick before the astronauts aren't in the window anymore to do the thing. We don't have to worry about that no more. At least not in that circumstance. All right. So now I have 3 times log base b of 2, because I brought the power down, plus log base b of 3. But wait. Up here, I was told log base b of 2 is 0.356. So this is now the same as 3 times 0.356 plus, and then log of 3 is 0.565. And now that is something I can crunch. I could do it by hand, but we have calculators. Three times 0.356 plus 0.565, 1.633. All right. Now this log base b of 4/9 I made up, so the answer is probably not going to be as pretty, but it is still workable. Well, no, it will, because we're going to have a difference. Difference still works out to the same number of decimal places. So I take that back. It does work out nicely. Meh. All right. So log base b of a fraction, split it into 2 logs that now have subtraction. So log base b of 4 minus log base b of 9. But I know 4 and 9, those should be more comfortable numbers now with all the exponent and quadratics we've been doing. That's 2 squared and 3 squared. And indeed, we are going to power down. And now it looks quite similar to what we had in the previous step. So 2 times log base b of 2 minus 2 times log base b of 3 And now I can substitute in my ugly looking decimals. So 2 times 0.356 minus 2 times 0.565. And crunchy, crunchy, crunch. Clear 2 times 0.356 minus 2 times 0.565. When we do get a negative, we can have negative exponents though. Negative 0.418. Now back in the day, you would actually have a table that would have like 20 of the digits for what like log base 3 of 2 was. And you had to figure out how many of those digits you needed to make sure that the result you got was going to be precise. But you didn't want to use too many because then you're wasting time on a level of precision you didn't need. This is the joy of having a calculator that can just crunch it. But still, that idea of significant figures does kind of show up because it's the degree of accuracy you have in a scientific experiment. So the concept behind it is actually still good. It's just not as mathematically intense as it used to be. All right, so I pulled this straight out of the book because it talks about the calculator keys. So you got a log key now and the natural log key. Those are the only two you get, and those are the only two you need. They are the most common, but we will have the occasion where the computer will ask you to calculate a different log. And we could calculate log base 3 of 2 as some ugly number between 0 and 1, because 3 to the first is bigger than 2. All right. So they just kind of put it out there, but I want to talk about, they also did a proof in the book. So A is not 1, B is not 1. That's just because these are bases, and if they're 1, lots of stuff like just cancels magically. All right, so they start with this interaction, setting up that y is going to be equal to log base b of x. If that is true, then I can rearrange this into the exponential form, which remember I do the way by using the actual function, applying it on both sides, and this is now b to the y is equal to just x. Now, the fanciest way to do this would be to use log base b on both sides if I want to solve for y. But I don't have a log base b on my calculator. So I'm going to use something I do have on my calculator. We can either do it with base 10 or base e, so either regular log or natural log. Really doesn't matter. I'm going to go with regular log. So I'm just going to apply log base 10 to both sides. And then your next lesson is going to be log equations, and this is something we're going to use on log equations. So now log base 10 of b to the y equals log base 10 of x. All right, now I know my power down. So this is now running out of room. All right, this is now y times log base 10 of b is equal to log base 10 of x. Now, log base 10 of b is a thing kind of like the square root of b or b to the 10th power is a thing that's being multiplied to y. So then it is a thing I can divide both sides of the equation by. Logs themselves don't ever equal 0 because the range is 0 with the curve. It gets really close to 0. We get a lot of fractional exponents, but we don't get 0 as the result because the exponential function, all the results are always positive on it. So this is permissible to divide by on both sides because it will never be 0. And now my exponent that I had before, my y, which is really log base b of x, is equivalent to, or computationally the same as, log base 10 of x over log base 10 of b. So log base b of x is the same as log base 10 of x over log base 10 of b. And that is what you can use in your calculator to crunch any of these ugly things. All right. So in the homework, there might be one where they give you change of base. Really though, it's later on, like if I wanted to graph these, in Desmos, yeah, you can just log base, I put in whatever number I want. On your TI, it's not so nice. Sometimes you can go digging through the catalog to find it, but just using the change of base formula works just as well, and you don't have to go digging for some obscure function. So the change of base formula to approximate log base 6 of 24. So log base 6 of 24 is the same as, I'm going to have log of 24 over log of 6. Now, technically, you could do it with any log base you wanted, like the natural log or log base 3 or whatever, but we don't have log base 3 on the calculator easily, so I would either go with log base 10 or natural log. And now, as long as we make sure we have careful parentheses, so when you do this, so on some calculators, when you type log, like on my phone, it opens a parenthesis. So let me sketch those in. The phone is going to open those, which means I am responsible for closing them at the correct time. So the log of 24 should happen before the quotient, but if you're worried about it not happening before the quotient, you can do some extra parentheses. And then it gets kind of tedious. That's why I was using the multiple colors, but like old school calculators, you had to be that like, let's put this in parentheses so you don't screw it up, calculator. All right, so log of 24 and close it, divided by, open it, the log of 6 and then close it and close it. And we got 1.773756, blah, blah, blah. 4 decimal places. 1, 2, 3, 4. So the answer we would type for Alex then is 1.773, and it stays 7. Now, you might be thinking, well, what if I use natural log, Liz? All right, let's do it. ln of 24 divided by ln of 6. Same thing, 1.7737056,145. Same thing. So the log of 24 is not the same as the natural log of 24. Those two numbers are different. The log of 6 is not the same as the natural log of 6, but the quotient between the two, the ratio between the two, will be the same. So it's kind of like saying if I have 5/3, and then if I double that, it'd be 10/6, like double the top and the bottom. So we know 5/3 is the same as 10/6, but 5 is not the same as 10. 3 is not the same as 6. Same idea here. The fractions are the same, even though the tops and the bottoms are not identical. Now, if you do want to graph these, like on a TI, that's what these are pictures of. Use the change of base formula. So to graph log base 2 of x, you would do log of x, notice the close parenthesis, over log of 2, close parenthesis. And that is all of our crazy log properties. All right, next week, We're going to learn about log equations. You are more than welcome to come and talk to me. I love playing around with those and solving them because they're just so wacky and I find it fun. Hopefully I will see more than one or two, please.